in this 7.7 section, we are only interested in really approximating the area. So that's the real topic at hand here. And in addition to the left endpoint approximation that we had discussed on the previous video, as well as the right endpoint approximation, we actually are going to learn about three new approximation techniques. We have the midpoint rule, and that's going to be abbreviated M sub n. We're going to learn about the trapezoidal rule in a subsequent video. Trapezoidal rule, and that's abbreviated T sub n. And then we're going to learn about something called Simpson's rule. And that's approximated with S sub n. And in all three of these cases, n represents the number of subintervals we have. Okay, so let's take a look at this midpoint rule first. So before we get started, I wanted to mention that approximations are not useful unless we know the amount of error there is in our approximation. So not only am I going to give you the formulas for our different approximations, but I'm also going to provide an error bound for each of these rules. Okay, so with the midpoint rule, we're still approximating with rectangles. So we're still going to have n rectangles. Okay, and if you look at the picture I have on the right over here, I actually have 4 rectangles. So here's the first rectangle, here's the second rectangle, here's the third rectangle, and here's the fourth rectangle. All right. And what you'll notice about these 4 rectangles is I don't evaluate at the left endpoint. I don't evaluate at the right endpoint. I'm actually evaluating at the middle of each subinterval. So I hope you can see that. Here's the second subinterval. I evaluate my height, the height of the rectangle at the middle. Here's the third subinterval. I'll evaluate the height of the rectangle at the middle. Here's the fourth rectangle. I'll evaluate the height at the middle. So we're going to label those midpoints of each rectangles M1, M2, M3, and M4. Okay. So how does our approximation work? Well, as I had mentioned to you earlier, this approximation is known as M sub n. And basically what we're going to do is the width of the rectangle remains the same. So we're going to leave a delta x there. And we're going to add together all of the heights of each of the different rectangles. So the height's going to be given by the function value, and it's evaluated at really x1 bar. So this x1 bar is the same thing as m1 over here. So maybe I should label that as a x1 bar, like this. This notation kind of comes from statistics. You know, in statistics, we have x bar is the sample mean. So this is like the mean of the two endpoints. That's going to be the midpoint there. All right, so we have to do that not just for the first rectangle, but for all the rectangles, all n rectangles. So we're going to have a x, the last one, the last height will be f of xn bar. Okay, and that's the formula. Now, how do we write down what our sample point is? Well, our xi bar is just going to be the average of those two endpoints. So it's going to be xi minus 1 plus xi, all divided by 2. And as usual, our delta x is going to be the width, which was b minus a, all divided by n. Okay. Now, as I had mentioned earlier, our approximation is not useful unless we can bound the amount of error. So let's write down error bound for this midpoint rule. And I'm going to call the error E sub m. And I'm going to put absolute values around it because we don't know if it's going to be an overestimate or an underestimate. So this is the amount of error right there. And this is bounded from above by a number. Now this number involves a constant k times, we're going to take the width of the interval b minus a, and we're going to square that, and then we're going to divide by 24 times n squared. Now what is this number k? This number k is a constant where we bound the second derivative of our function on this interval. So we have a closed interval here. As long as f is continuous, we can find out what the largest value is. We're actually not bounding f, we're bounding the second derivative of f, and we'll just got to figure out what that absolute maximum is. And whatever that absolute maximum is, that goes as part of our error bound formula. This n, just as a quick reminder, that's the number of rectangles. Okay, so we'll be working on problems where we use technology to find our estimate, and we're basically going to use this formula to find our estimate. And then once we bound the second derivative, we'll be able to bound the error as well. Okay, so this is it for the midpoint rule. Next video, we'll look at the trapezoidal rule. Take care, everyone.